So is the whole class here? The whole diploma class, or anyone is missing?
Yes.
Yes. If someone is missing, I will go grab them and force them to be in my class. All right, so everyone is here. Voluntarily, let's keep it real. I mean, I'm telling you here voluntarily. Don't forget that once you start crying about this class. But no, jokes apart, this is going to be a very fun class, I hope. So this is our functional analysis class.
Functional, fun.
Fun, not functional analysis, yes, it's going to be fun. 2019, very nice. So, as you know, this class is intended to be of 20 lectures of roughly 1 hour and a half, give or take a little bit. It starts today and it goes to the beginning of April. I decided to do 2 times a week instead of 3 times a week, so you guys have more time to absorb and study and think about potential homework problems that will be assigned, discuss with your colleagues, and come to me, ask questions. And so I think there will be more time for you to dive into the subject and take more of this class. So what do you need to know? Okay, so this is somehow a small blackboard. Can anyone read this size? That's okay, right? So I will be your instructor in this class. This is my first class here at ICTP. My name is Emmanuel Carneiro. You can just call me Emmanuel. I joined the faculty of ICTP last October, so I'm here roughly the same time as you are. So I came here on October 1st. I'm completing 4 months here. Before coming here, I was a professor at IMPA in Rio de Janeiro, Brazil, for the past 8 years. So I got my, I'm from Brazil. I got my undergrad and master's in Brazil. Then I went for a PhD at the University of Texas at Austin in 2005 to 2009. I graduated, I got my PhD in 2009, so roughly 10 years of PhD now. I work roughly in the field named analysis, and I want to emphasize analysis in the broad sense. And I will try to convey along this course for you little bits of what I call analytical ideas, which I find the field very beautiful and very, big in terms of possibilities. It's more of a way of thinking than some specifics per se. So you gain a way of thinking about problems, and you can communicate with people in different fields which are not very far from analysis, people from probability, partial differential equations, number theory, mathematical physics. So once you have the whole toolbox from analysis, that's what I find fascinating. You get to communicate to a lot of mathematicians. Let's say, after I got my PhD, got postdoc positions in Princeton, spent 1 year out of the academic world when I came back to Brazil. This is a story for another time. And then I joined IMPA in 2011 and stayed until 2018. And then came here, all right? Let's see, what I hope to achieve in this course, besides, of course, getting to know you very well, and I hope that you will not dislike me very much at the end of the class, but I want you, I promise, actually, it was a promise to you, that you will learn something from this class, okay? The amount of something, it actually depends on you, because I am a believer that here in any class that you take in mathematics, I just do 20% of the work. So 80% of the work is for you to do at your own pace, and how much you want to do, it depends on you. I will be available to talk and to discuss the problems, but mathematics, I mean, it's just sometimes you sitting down in the chair and working out to understand the subject. And hard work. I'm a huge fan of hard work. For me, hard work beats talent when talent does not want to work. So keep this in mind. And then, well, I have a particular style, but not sure if I will come with it with full force. I usually like homeworks and exams. I somehow come from this American school that we as students, when I was a PhD student, I used to work hard. There's a lot of, the amount of work was big when I was a student. I'm not sure if I will do this here or not, but it has certain advantages and disadvantages. But I really expect, since I'm getting to know you for the first day and you're getting to know me from the first day, so what I expect from you is total honesty, participation in the class. Let me know if I'm being too fast or too slow. So let's keep in synchrony, let's keep in touch between what we can do, because there's no point in mathematics one cannot give a step which is larger than what you can. So you have to move fast, but fast in a pace which you actually can follow things through, right? So this is my intention, that everyone here will understand. So we'll start relatively slow and build momentum, and then people getting more comfortable, and I hope you will enjoy the subtleties of analysis. Anyway, so what else do we need to know about the course? So as I told you, this course is intended to have 20 lectures. You do have a final exam here, right? And as I understand, I am allowed to make perhaps other exams along the course if I want. So I might do maybe let's say a bit of homework. Your grade will be a little bit of homework, maybe midterm exams, midterms, maybe 2 exams, plus the final. Study hard and you will be rewarded. Books. I brought this particular book that I like on functional analysis. Is this book by Brazis. I brought it here for you so you can take a look. So this would be the main reference of the course that I would suggest, but I think that the classes here will be self-contained, and if you just want to take notes, you should be fine, right? But you should have some book of functional analysis to study from. What I'm going to do is not going to be 100% here, but I want to do maybe 70% of what I want to do is here, and the rest I will bring some other topics from the outside. So let's say this book by Brazis. See, I'll write down the title here: Functional Analysis. Sobolev spaces. And partial differential equations. Okay, but feel free to also consult other books. Okay, there are several other classical books in functional analysis and in real analysis that you can feel free to take a look at any other book that you may want to. So what I expect from you is that maybe you have a main reference. I'll keep roughly the outline of this book in terms of the order where we'll talk about things, but then you go and you consult with other books that you may have. It may be helpful to solve an exercise, it may be helpful for you to understand something else. Don't be limited to what I say, go and dig deeper on your own. Start, the critical thinking starts now. I mean, the quest to become, go in your scientific career, starts with this critical thinking. Whenever you look at things, this curiosity should drive you. What else? As I told you, I want you guys to feel free to ask me questions here in the class, in the corridor, come to my office, discuss at any time. I won't set up any sort of office hours, so just show up in my door anytime that you feel like. If you have a question, if you want to talk about math or life, if I can help, I will. I'm a huge fan of collaborative work, so I really encourage you to work in collaboration with your colleagues. So if I ever assign you homework, I have no problem if you guys get together to do the homework in groups of 2, 3, 4, or 10. That's perfectly okay. All I ask is that when it comes the time to write down the solution, you go to your place and you write down your own solution that you may have learned from somebody else or from the internet or from a book, but you sit down and you try to write down the solution yourself to make sure that you learn the thing, learn the subject, right? So don't fool yourselves. So it's okay to discuss, it's okay to have someone teach you. It's actually very nice if you know to teach somebody else that you learn twice. So this exchange of experiences is great. But when it comes to writing down things, you should sit down and write down and make sure that you understand these things, okay? I don't have yet a tutor for this class. I'm searching, we're having a bit of a shortage in postdocs in analysis here. But I will try to somehow amend the situation by next week. Is that in your interest to have a tutor for this class or no? Yeah?
Yes.
The tutors help you a lot?
Depends on the person.
Okay. And, okay, so maybe by next week I will have some updates on that, okay? Our course is going to be, by definition, the standard time is Tuesday and Friday at 4 p.m. There will be some changes. For example, next week, I guess we have a change. Our next class is not Tuesday, but it's Wednesday because of the Salam lectures that will take place here. So let me start. So next week, our next class is Wednesday and Friday at 4 p.m. And then I have one upcoming trip in the next week, and I will keep you updated. But starting on the next 2 weeks, we have these changes, but since starting in the third week from now, this will be pretty much our time, okay? If there's need for any change along the way, of course, I will consult you. We'll find the best way to put together a class, makeup class. Okay, I expect to be getting to know you along the way. We had a little bit of chance to interact before, but now I want us to interact more and more, not only mathematics, but as I told you, if I can help you in any way, I will. I hope to convince you, some of you at least, to get the flavor of the subject and to be interested in studying analysis as you go in the future. At this particular stage of your life, where you're taking these graduate courses, you're learning about several beautiful subjects in mathematics, and it's perfectly okay to not being able to decide because everything is so beautiful and you love everything. That is what it's supposed to be, because what you're learning is like mathematics, the most beautiful parts of each topic in mathematics that were transformed in the best way possible to be presented to someone who's learning the subject now. So if you learn the subject of analysis and real analysis, you learn about the Lebesgue measure. If you learn Galois theory, if you learn complex analysis, beautiful. Differential geometry is beautiful. Why can't you draw a map in a piece of paper which is flat? I mean, these sort of theorems are just beautiful, and most of the subjects are beautiful at this stage. At the next stage, then you will start to realize that there are things that you like better than other things. Well, this is maybe still beautiful, but too hard for me, or then I don't find this particularly beautiful, and then you find yourself going up the ladder and deciding if you have more of a mind to be more algebraic, or more an analyst, maybe some topological, you know. The analysis philosophy is a bit different from the algebraic philosophy. Here, we live in a world which is essentially an open set of ideas. There's no one particular way to find the solution of a problem. There's usually possible multiple ways to massage things and go and dig a little bit deeper and move forward epsilon by epsilon, then you find the solution. You know, there's no one way. So if you find that way, you get it. If you don't find it, you'll never get it. It's not a yes or no statement. There's always, so life here in this class will always be an open set. You know, people may approach things in different ways. Okay. And of course, to start the class, this is my first question for you. And I have to understand you as much as you understand me. So the class before here in analysis that you saw complex analysis and you had a course in real analysis. So where did you stop in real analysis? Can you tell me how was your real analysis class? What did you learn in real analysis so I can start perhaps from there? What do you think? Can you give me an overview? How was your real analysis class?
We start maybe just after reviewing absolutely continuity of the fundamental theorem of calculus.
Okay.
In one dimension.
Yes. So, but you saw how to define measures abstractly, measurable space.
Yes, and only an introduction. Not only an introduction.
Did you see LP spaces?
No.
You didn't see LP spaces in this real analysis
But
class.
we know how to integrate at least absolute value function, because we know what is measurable, what is integrable.
You know what a measurable function is. You know what a measure is in
How
a,
to construct.
in a space. You know what a sigma algebra is. You learn the basic theorems of integration, monotone convergence, dominated convergence. Okay, and then you were perhaps studying bounded variation, absolute continuous functions. Go ahead.
So it's basically just integration and differentiation in real numbers, but the approach was can be generalized quite easily. So it was not, for example, we defined the measures in a very the outer measure and the things. It was not very restricted to real numbers, so we're somewhat exposed to the ideas.
Okay. Let me make it clear to you from the beginning that my goal here is not to teach you everything that I know or everything that there is to know in analysis or functional analysis. What I will do is perhaps choose a selection of topics which I find particularly important, and we will discuss at length these things. But most of all, what I want to pass to you is this idea of giving you a background, giving you something to build on so you become confident enough with these tools that you have acquired here to go and study everything. You know, it's like giving you a backbone of a skeleton, and then you will, of course, grow as you want to grow. But I just want to give you some tools which I find fundamental, and there's no point in being extensive here and we study the detail of the form of this theorem. No, I want to give you the main ideas on the main subjects, and then when you study on your own, you have the chance to branch out and learn the complement things. So this is why I'm thinking it's so important for you to do your own study at your own time to complement what we get here. Okay? All right. So the basic overview for this class. There is a classical program in functional analysis where you find in many books. I will roughly follow these things, but I want to give you little bits of ideas in what I call, let's say, general analysis, maybe real analysis if you want, harmonic analysis, so you can get the flavor of these things too. So we'll talk a little bit about LP spaces. I could talk about this later, but I want perhaps to start with this because this will be a source of many of our examples that we're going to be discussing. Then I want to talk a little bit on how to approximate functions by other functions, doing convolutions, approximations of the identity. Then we're going to move slightly to the basic main theorems of functional analysis on vector spaces. Hambana theorem, closed graph theorem, open mapping theorem, these sorts of basic theorems. We'll learn a little bit about strong topologies, weak star topology, compact sets. Then we'll be back to LP spaces to talk a little bit more. Then maybe perhaps study a little bit of Hilbert spaces at the end and some compact operators in the end. Okay, so this is roughly the sketch. So this book here is not meant to be studied complete. As the title says, it's a book about functional analysis, solid left space, and partial differential equations. So there may be 3 courses here in this book. So we will be taking a look at chapters roughly 1 to 6. Perhaps if you want to take this book, chapters 1 to 6. Our course will be inside this, plus some additional topics. So let me just point out here, I will only be looking at chapters maybe 1 to 6. All right. Questions before we start? Are we still excited?
Yes.
Good. I like it.
Excited?
Yeah.
More excited.
Oh, more excited. This is what I want to hear, man. Good. Good. Okay. So, topic for the class today. Let's start talking. And hopefully in this class I will give you an idea of why I like analysis a lot. Let's see. Class number 1. I guess I can erase everything here and start from. You will say I like to number my classes and give them titles. So this will be class 1, and we're going to talk a little bit about LP spaces. Okay? So, the whole setting here, I will be working on a certain space, which I call omega, with some measurable sets that I have defined, and a measure mu. So this is usually the triple space, measurable sets, and measure. Okay? If you say, Professor, you know, I didn't understand too much, and I just learned the Lebesgue measure on RD, that's fine. Okay, so if you want to think about it, if you want to think about RD, if you want to think about the Borel measurable sets, that's fine. And if you want to think about the Lebesgue measure, that's fine. Okay, so imagine that you are on this setting. For a given exponent, so you learn how to integrate functions, you learn how to integrate. First, when you learn the theory of integration, you learn how to integrate non-negative functions, right? You approximate the non-negative functions by characteristic functions of sets, and you build up, and essentially you define the integral of that function as the supremum of all the characteristic functions of linear combinations of characteristic functions of sets that are below. This is how you integrate positive functions. To integrate functions that have positive and negative part, you just split the positive part and the negative part, you integrate the two of them separately, and then you subtract, provided that it makes sense. You're not taking infinity minus infinity. You may integrate complex variable functions the same way. You will divide the real part and the imaginary part, the positive part of the real part, the negative part of the real part, positive part of the imaginary part, negative part of the imaginary part. So, but for us, let's just, for the sake of simplicity, let's work with functions f of omega into, say, r, which are measurable. Okay? And then the class LP, so given a number p, which is between 1 and infinity, and here I include 1 and I include infinity, I will define a space. Let us define the space, which I'm going to call LP of omega, as being the space of functions f from omega to r Here, if you want to put C, that's fine. If you want to take complex valued functions, so let's say f of omega to r, measurable functions, okay, such that this so-called LP norm which is just the integral of f of, say, x dux. Is fine. Okay?
For P,
Let's say for P less than infinity. This is the definition. Okay? These are the measurable functions such that the LP norm, which I define like this, the integral of absolute value of f raised to the p d mu of x, everything raised to 1 over p. So whenever I talk about the LP norm, I mean this object. Okay, so this is the space of all functions such that this is finite. Okay, so you take all measurable functions that have the LP norm finite. We will have some work to show that this is actually a vector space, that you can actually take two functions and add them up and you still fall in the space. And that this is a norm. Okay, so this is actually a normed vector space. And this is a little bit more, this is a Banach space, which means that this is a complete normed vector space. Okay, so this is the first thing that we want to learn. When p is equal to infinity, you have a definition which is slightly different. So these are the functions f, so the space L infinity of omega are the functions f omega to r that are what we call essentially bounded. Meaning that the norm f, norm at infinity of f, is just the, say, infimum over all quantities c bigger than 0, such that f of x is less than or equal than c for almost every x. Okay? When you learn measure theory, you guys learned about the concept of almost everywhere. So whenever I talk about this, I'm saying that sets of measure 0 are irrelevant for our purposes, okay? So when I mean that the function has to be less than or equal than a certain c almost everywhere, and the infimum of such c's, such that this holds, is the L infinity norm of my function. So my function is essentially less than or equal than this number, except on a set of measure 0. Okay? Sometimes you will see me doing some slight abuse of notation. So when I write LP norm, of course I mean the LP of omega. When I say almost everywhere, of course I mean mu almost everywhere. So it's almost everywhere with respect to this measure mu that I'm working. And most of the times will be, say, Lebesgue measure on RD or Lebesgue measure on a subset of RD. Most of my examples will be, or maybe counting measure on a space of sequences. But these are my definitions of these spaces. So far, what I have defined for you is just I have defined sets. Okay? So it's you can think about these spaces as subsets of the sets of measurable functions, all right? That they have this particular quantity bounded or this particular quantity bounded. So LP is the guys that are essentially bounded. In other words, that this number here is finite. Okay? Good. So tell me something non-trivial about these spaces. what would you like to know about these guys, or what would you like your colleagues to know about these spaces? Let's start from the beginning. Like I said, why are these vector spaces? So I'm going to my first claim, my claim one, let's say, is that this LP of omega is a vector space. Recall what's a vector space, right? A vector space has essentially two properties. So for a set to be a vector space, it has to satisfy two properties. I need to be able to multiply by a scalar on the field of scalars that I'm considering. Let's just say we're working over R here. And I need to add up elements, okay? So every vector space is associated two operations, one of sum and one of multiplication by a scalar, okay? So, of course, if f is a function in LP and lambda is a real number, then lambda f is another function in LP, right? So if I multiply by a constant lambda, it's pretty straightforward to see that the LP norm of lambda f, this lambda here, it goes out of the norm with just the absolute value of lambda. Okay? If you just multiply by lambda here, you have lambda to the p to the 1 over p. But the modulus of lambda. So if you multiply by -1, it has the same norm. So this means that multiplication by a scalar is no problem. Now, the other thing that I want to discuss with you is that if f and g are both functions in the space LP, why does the sum belong to the space LP? Why?
There are some inequalities. Minkowski, all the rules.
All right.
Allows to define. But it's the norm of f plus g and p.
Exactly. But maybe before Minkowski, if we can go really simple, you can just use an inequality like this, right? F of g plus f of x plus g of x raised to the p.
Less than the 2 of the maximum?
I would say less than 2 to the p times, right, f of x to the p plus g of x to the p, right? For example. Is that clear to you all? Because f plus g is less than 2 times the maximum. Then I raise to the p, p times the maximum raised to the p. And the maximum loses to the sum of these two guys. Okay? So if the integral of this guy is finite, the integral of this guy is finite. And when I sum up, the integral of this guy is finite. Okay? So a pointwise inequality like this establishes that if f and g belong to LP, then the sum belongs to this space. Okay? Recall that this space is a space of measurable functions that have certain norm, certain quantity bounded. So in principle, I could add two functions and this guy becomes unbounded, but this is not the case. Okay, so this is the first thing. This is a vector space. Now, I want to move forward and try to prove that this guy is actually a see, I didn't say, but when we look at this space, well, we're going to see in a bit that we have to look at it modulo sets of measures 0. Okay? So I want now to, maybe after here, I want to show that what we defined as the LP norm is in fact a norm. So that this is a normed vector space. Right? But maybe first of all we should talk about this Holder's inequality. inequality here. So whenever I have an exponent p, I will always denote by p prime the guy that is the conjugate of the exponent p. Conjugate in this sense. P prime will always be the guy such that 1 over p plus 1 over p prime is 1. So these are called conjugate exponents. Okay? And one of the nice inequalities, perhaps the first inequality that should go into your toolbox, into your pocket, is this Holder's inequality. That says essentially the following, that integral of fg, and forgive me, I'm not going to be integrating over omega, or x, but the mu of x, I'm just going to write like this. Integral of fg loses to the integral of f to the p. 1 over p, integral of g to the p prime, 1 over p prime. So in other words, i.e., if you want, the L1 norm of fg loses to the LP norm of f, L p prime norm of g.
This is the absolute value of f.
You can put the absolute value of fg, but this certainly loses to the integral of the absolute value of fg.
But this way we don't know if the absolute value of fg is bounded by the LP. This is strong.
No, well, it's the same, right? Because you can, if this inequality holds for all f and all g, you can just replace f by absolute value of f and g by absolute value of g. Okay, so it's essentially the same. But yeah, but it doesn't make, you can put it if you want. Okay, how do we prove that? Jensen's inequality. Could be, yes. How do you suggest that we propose? That we proceed on this regard?
First, we need to prove a to the maybe some basic inequality. For example, a to the p over p plus b to the p over q, p prime over p prime is bigger than a, something like that. We need to prove this by Einstein's inequality. After that, we can prove this inequality.
Good, good. Exactly like this. You know, I was thinking about this yesterday when I was coming back from, I was in Munich this week to give a seminar, and on the way back I was, okay, let me think about if I can reproduce all this theory about LP spaces, and I got, how do I prove this inequality? And I started writing down, and then I'll show you in a bit the computation that I did. But what I find beautiful is that, as I said, there's no just one particular way of doing these things. You will find your preferred way, and there are multiple ways of approaching this problem. Let's maybe discuss one possible way. You see, whenever you want to prove this inequality with p equals 2, so if p equals 2, p prime is equal to 2. So this is usually referred as the Cauchy-Schwarz inequality. Schwarz, right, which is just the statement that fg loses to the integral of f squared to the 1/2 squared to the 1/2. So this is a particular case of this guy, okay? Whenever you write Schwarz, or you read Schwarz, actually, because he was German or from Austria, I don't know. The name has no T. It's Schwarz with Z. There's another Schwarz that you'll see here appearing, which is Schwarz with a T, which is a French mathematician, Laurent Schwarz, which lived 100 years after Hermann Schwarz. So do not make a confusion about these two guys. One is responsible for the Cauchy-Schwarz inequality, or the Schwarz theorems in complex analysis. This is a recent guy from the distribution theory, the Schwarz class, and so on. Okay, this is a very common mistake in mathematics that I get when I referee papers. People write in the inequality Cauchy-Schwarz with T, and I always write down this little historic note saying, hey, by the way, the Schwarz doesn't have T. If you wanted to prove Cauchy-Schwarz inequality, there is an easier way to think about it. And let's see. And perhaps the easier way to think about this is to actually consider the L2 norm. See, one possible idea to prove this is to consider the L2 norm of this function f minus lambda g, L2 norm square. So I'm going to take the L2 norm square in order to remove the exponent on top. This is just the integral of, let's say, f minus lambda g squared. Okay? We're talking about real numbers here. So something square is always non-negative. So this quantity here is obviously non-negative. Right? For any lambda that you want to put here. So I fix f and g, I fix two functions f and g. Now for any lambda that you put here, there is no question this integral will be a non-negative integral. And then you open up this thing. So you open up, this is f squared minus 2 lambda fg plus lambda squared g squared. Okay? The integral has this nice property that it's a linear operator, so you can move it here. So this integral is just the integral of f squared minus 2 lambda integral of fg minus lambda squared integral of g squared. Are we all right? Do we agree? Now, you have now a quadratic form on the variable lambda. Lambda here is a real variable. You have a quadratic form in the variable lambda that you have three numbers here. Integral of f squared, integral of fg, and integral of g squared. No matter which number lambda you plug in here, this will always be a non-negative quantity. So if you have, say, a lambda squared plus b lambda plus c, bigger or equal than 0 for all lambda, this equation has no real roots. Right? So if it doesn't have any real roots, there is something that must be said about the discriminant of this guy. The discriminant, well, you learned this in high school, right? Discriminant b squared minus 4ac is not positive, right? It's negative. Okay? So if you now interpret this with these coefficients, this is your a, this is your b, 2 times this, and this is your c. So what you get is delta in your case is b squared is just 4 times this minus 4a times c. Is less than or equal than 0. This is the inequality. This is Cauchy-Schwarz inequality. You eliminate the 4, you move things to the other side. This is what you get. Now if you take square roots on both sides, this is Cauchy-Schwarz. Okay, so this is a very clean, nice way to prove the Cauchy-Schwarz inequality just using the fact that you know something about quadratic equations. Such a clean method is not entirely good to deal with the general P case, right?
Or is it?
Yeah, I don't know, right? So maybe if you wanted to do P equals 4, you could do something similar, but you know, this is the beauty of things. You know, these things works so nicely, but on the other hand, doesn't generalize. And then you have to look for another way of thinking for this problem. And the way of thinking is like he said, using some sort of convexity inequality. You know, the whole point that we used here in this guise was this arithmetic mean beating the geometric mean inequality. If you want to put it like this, if I write this inequality, everybody will believe me, right? That a squared plus b squared is bigger or equal than 2ab. Sometimes arithmetic mean bigger than geometric mean inequality, or any name you want to give it to this. But this inequality is something that I can potentially tweak a little bit and make it to accommodate to my exponents p and p prime. Because there is a slightly modified version of this. So now let's try to prove, for example, that for any real numbers, let's say a and b positive numbers, you have that ab is less than or equal than a to the p over p plus b to the p prime over p prime. Where again, p and p prime are conjugate exponents. And let's say they're not infinity. Because this inequality here, if one of them is 1 and the other is infinity, then it's easy to settle this, right? The L1 norm of fg loses to the supreme, if you want to take the supreme norm of g out, so it's just the infinity norm of g times the L1 norm of f. Okay, so if one of these two is infinity, you're done. So you just have to worry about the case, legitimate case where p is between 1 and infinity. All right. So suppose I want to prove this. And then you can, again, invoke your favorite tool to prove this. We could, for example, use a little bit of calculus to show this. All right? So let me, for example, assume without loss of generality that a to the p is less than or equal than b to the p prime. Okay, that this guy loses to this guy. If it doesn't lose, then I change the rules of a and b. But let's just say this. And I want to construct a function, say f of x, which is just going to be, I want to prove that this side is bigger, so let me just write f of x as, I'm just going to write with the variable. Think about the a as a variable. So I'm going to write it like this. Okay, so now I'm thinking of the number a as being a variable, x. And what I want to prove is that this function f of x is bigger or equal than 0. So what I could do is, I could look, when x is 0, when x is actually 0, I'm okay, right? This is 0, this is 0, and this is just a non-negative number. Okay, so I start good, and I just want to make sure that I keep good. I keep proving that. I want to prove that this function is bigger or equal than 0. So one way to see this is to look at the derivative. So if this is my function f of x, the derivative f prime of x is what? This x to the p goes down, so x to the p minus 1, minus b. Okay? So intuitively, if we wanted to graph this function, when x is 0, it starts as something positive, right? And then the derivative, when x is 0, is negative. The derivative is negative up to a certain point. So this function, this means that this function is decreasing. It starts here positive, and it's decreasing, right? That's okay. Now, let's see if this leads us to somewhere. So the derivative is negative all the way up to if I wanted to solve f prime of x equal to 0, I would get this as x to the p minus 1 over b, so x would be essentially b to the 1 over p minus 1. So up to this point,
Same point, this is a is equal to b prime, same.
aha, so this is, I'm assuming that a is less than this, right? Okay. Which means, so yeah, so as I assumed, right? So that, like I recall, as I assumed, so A was less than B to P prime over P. And here, recall that 1 over P plus 1 over P prime is 1, so you can actually find P prime in terms of P. And then you get that P prime is P over P minus 1. Okay, if you solve this. So this is actually this number. So I'm actually assuming that I am in the range between 0 and this point, the point where the derivative becomes 0. So my function is decreasing all the way up to that point, right? Now let's see what, if I just look at here, and then if I just plug in this number in my function, what happens with this number, f of b to 1 over p minus 1? What happens at this number, where the derivative changes sign? I just plug in the equation, right? So what is this? It's going to be b to the p prime, so that's already, you guys already know me what I have, plus b to the p prime over p prime, minus x times b. And x times b is b to the 1 over p minus 1 plus 1. So it's p minus 1, p, which is p prime. And what is this?
0.
Because 1 over p plus 1 over p prime is 1, so this, guys, is actually 0. So the value of the function at this point is 0. So this means that this is the point where the derivative was changing sign. The derivative was negative and it was becoming positive. And at this point where the derivative changes sign, what I do is I am touching 0, but here the derivative is going back again. So this is the graph of my function. The derivative is decreasing up to this point, which is b to 1 over p minus 1, and then it's increasing. And the value of the function at this point, I calculated and it's 0. Okay, so this is the graph of my function. By a little calculus, then the function is non-negative. The conclusion is my f of x is actually non-negative for any x, right? Well, I didn't even, this was not even needed. I didn't use, right? This was not even needed. Once I know that the graph of my function is like this, I just want to show that the derivative goes down up to this point and then goes up again. And at this point where the derivative changes sign, or my function starts to increase, the value of the function is 0. So the graph of the function must be like this, okay? So bottom line is that if you work your way through calculus, can be helpful in several different problems when dealing with inequalities in analysis, okay? If you phrase it the right way. Right, so you get this little fact here. And you see, whenever you work backwards, you can clean up your own proofs. Say, I assumed something here that I thought I was going to need, I didn't need this, and I didn't need this, so this is not, if you want to, you can erase this. Not needed, not needed. All right, this is how we're going to do things here. Sometimes it's always very beautiful when somebody presents you a proof which is perfect and he eliminated all the things. But sometimes I find it useful to learn the line of thinking, which is actually what normal people do, right? So we try something and then we don't do it, and we see what we have to modify and so on. So So you see some of these proofs that we're going to do in this course. I find it more interesting to show it to you the way that I think and get your feedback the way that you think, and we start thinking analytically. It's much more important than actually memorizing what's the right proof. Of course, in the book you will see this in the most beautiful way. Perhaps a more beautiful proof than this using calculus, but you see, this is like soccer. What matters is that the ball crosses the line and it's goal. Okay? Good. So once I have this inequality at hand, what can I do? Remember, I wanted to show holder, right? I wanted to show holder. I can integrate both sides.
And we can modify holder's inequality to be for functions of norm less than 1.
For functions of norm less than 1. Yes, you can
Less than or
dilate
equal to
them.
1, or equal to 1.
The absolute value, the pointwise absolute value of things? You mean?
I mean, I'll consider f over its norm, and it will be of absolute value 1.
You consider f, okay, yes.
We can put b in the integral of g,
Why
or
don't
the absolute
we-
value, and it's
Okay, what I wanted to do was actually, if I use this inequality, so okay, using this, what we would have is, we would have the integral of let's say, f of x, g of x, losing to the integral of f of x to the p plus the integral of g of x to the p prime over p prime, right? I just used it pointwise and I integrated. Okay. But you see,
without b, I think.
this is just pointwise and I integrated, right? So I apply this inequality pointwise and I integrate. Something is still on the way, right? In Holder's inequality, I don't have a product on the right-hand side. I'm sorry, I don't have a sum, I have a product. So how can I make this sum into a product?
Normalizing maybe
we
the
can
functions.
use this. We need to use from another way. Our inequality, Holder's inequality is stronger than this inequality.
Maybe
Yes, it's stronger than this.
we define
So,
f,
but we don't.
f capital like f, lowercase over its norm, we can use it because we can.
I think it will just be dilating things, but
We can assume, for example, integral fxp is equal to some m, and we can take integral gx p prime is equal to n, and we can take a in our equality a is equal to f over m and b equal to g over n. This is true.
yes. There is a little bit of a little bit more massaging that you can do here with this. And the little bit more massaging that one can do here, if you have an inequality like this, is that you could think of this inequality as, say, multiplying your a by a certain number lambda and dividing your b by a certain number lambda. If you multiply a by a certain lambda and you divide b by the same lambda, this side won't be affected, right? But then the other side will be affected. And then you may still, since this left-hand side will be the same and the right-hand side will be bigger than this for all the lambdas, and then you may try to minimize the right-hand side over lambda. So let's do this trick here. So what I want is to just multiply a by lambda and divide by the same lambda. So I'm going to consider here a lambda bigger than 0. And this will pop up here as lambda to the p. And this will be divided here as lambda over p prime. Okay? So this inequality is true. It's true because of the previous inequality. I'm just changing a by lambda a and b by b over lambda. So it's the same previous inequality used with two different numbers. But now I have a free parameter lambda here, which is very interesting. Now let's play a little bit with this, where lambda is any positive real number. again, I don't know if this is the easiest or more straightforward proof of Hölder's inequality, but you know, as I told you, there is value. I think there is value for you in starting to putting these tools in your pocket. Might be useful in other circumstances, right? So you have an inequality here where this side is fixed and this side here is always bigger than this for any lambda. So what you should do is, well, you should choose the best possible inequality, right? So if this holds for all lambda, I will try to minimize this side because then I'll have this as tight as possible. Okay? Of course, if my lambda here is infinity, it's meaningful, the inequality, right? Infinity bigger than something. Of course, I knew that. But then you have to optimize this inequality to get the best possible lambda here. And then, so you're left with something like, let's say, function g of lambda, which is lambda to the p times a certain number a over p, minus a certain number b, say lambda to the minus p prime b over p prime. This is the prototype, this is the function that you have here, where I have called this number here a, and I have called this number here big B, big A and big B. Okay? And now I want to minimize this, minimize in lambda. So there goes calculus again. Right? G prime of lambda is, I like to use calculus in this problem because you have also lambda p to the p and then this p cancels. So you get lambda p minus 1 times A minus, and then this becomes minus p, goes out, lambda to the minus p prime minus 1 b. So if I want to make this equal to 0, I would get what? I would get that lambda over p plus p prime. So if I move this to the other side, it would be just b over a. Is that right? So if I move this guy to the other side, and then lambda to the minus 1 cancels here, lambda p plus p prime b over a. So this is what lambda is. Then you have found the lambda. And this b over a to the 1 over p plus p prime. Va bene? Good. So this is the minimum lambda, because of course this derivative, when lambda is 0, it starts negative. When lambda passes a certain threshold, it becomes positive. So if the derivative starts negative and becomes positive, this function is decreasing and then increasing, so there is a minimum, and the minimum is attained at this point. So the minimum of g of lambda, right, is equal to, I just plug in this point here. So this is b over a 1 over p prime plus p prime over p plus lambda, so b over a, I'm sorry, this was raised to the p, right? So this is lambda to the p, and this is lambda to minus p prime over. Okay.
There is a in first.
There is a here, yes. Thank you. Okay. Now it's just a matter of having faith. So if you didn't do anything wrong, things should work out fine. Let's see. Let's see. How many b's do I have here? So I have b to the p over p plus p prime. How many a's do I have here? I have a to the 1, so 1 minus p. So I have a p prime, so over p plus p prime, right? This is the b and this is the a that I have. Over p, and again here, how many b's do I have? I have 1 minus this, so I have p plus p prime, and I have a to the minus minus, so it's p prime over p plus p prime. So I get the same thing, right? P prime. So when I get the same thing, 1 over p plus 1 over p prime is 1. Now, there is some simplification that I can get here. What's this exponent here?
1 over p prime.
So, p over p plus p prime is 1 over p prime. Is that true? Because if I just invert this fraction here, the inverse of this fraction here is just 1. Yes, so if I multiply here, this is 1, right? 1 over p plus 1 over p prime. So this is 1 over p prime. The same thing that this is 1 over p. Okay, so this is what you get. Beautiful, because we found out that the minimum was b to the 1 over p prime and a to the 1 over p. Who was a? This was my a. So the minimum of this, so this implies when we minimized in lambda, implies that the left-hand side stayed the same. It is the right-hand side in its minimum possible value, it's still bigger than the left-hand side. And in its minimum possible value, now there is a product that appears here. It's a to the 1 over p, so it's just a. A was this to the 1 over p, and b to the 1 over p prime. And this is Holder's inequality. Okay? So, from now on, you have this in your toolbox. So you should face these courses like a little bit like a video game. So one of these first-person shooting thing that you go and collect weapons along the game, and you just start with a little knife, and then you get something else, and then you get something else, and then you get something else, and you become more and more powerful. So this is it. So everything that we discuss here, you learn, you're now allowed to claim this inequality forever in your life. And everybody in this class has to understand what it is, how's the proof, and everybody has to know. So whenever I say by Holder's inequality, everybody knows what I mean. And you're okay with that. Okay, one more weapon for your toolbox. Questions, guys? You see. Now go to the book and take a look at what's the right proof. Probably not this one. We used a little bit of calculus here and there. So this is a very, human-like proof. But this is a little bit of what the philosophy of studying analysis is. You first do a proof, you get yourself convinced that something works, and then you start to try to polish things and make things in a nice way. Okay, maybe I should not have erased it. Questions so far? So we proved Holder. Now, I wanted to discuss, let's come back to our discussion, and we were proving that this guy was the LP. I told you it was a vector space. I wanted now to show that it's a normed vector space. Aha! This is why I wanted to present to you Holder's inequality before. But let's come back to the point that LP is a normed vector space. In other words, what I want to show is that this little object here is a norm. Do you recall what the norm is? What does the norm has to satisfy? Remember?
Non-negative.
It's non-negative, so this norm is certainly non-negative.
Negative precisely function is 0.
Okay, so let me first write like this. This norm is usually when I multiply by a scalar, what has to happen, guys? This guy has to be out, right? With the absolute value. So this check. Second property is that the norm of a function has to be bigger or equal than 0, and if it's 0, this implies that the function is 0. Right? it has to be always non-negative, and if it's 0, this implies that the element should be the 0 element. This,
If and only, or does
well, okay. This is what makes us, if you wanted to really talk about a normed vector space, then we have to make sure that we just work with disregarding sets of measure 0. Okay? Because otherwise this wouldn't be true. Okay? Because this LP norm or any integral doesn't see sets of measure 0. Okay, so if you give me a function which is 0, 0, 0, and at the point 0 is 1, the integral will be 0 of this function, because it's just 1 at the point. And if you don't say, well, but this function is not the 0 function, you're right, it's not the 0 function. Right? So this is why you have to consider it as 0 functions. So functions which are 0 almost everywhere are 0. In other words, when working in these LP spaces, if two functions are equal almost everywhere, I will actually tell them that they are the same function in the space. So I will consider the class of function modulo the sets of measure 0. Okay? So now this becomes true. A function has LP norm 0 if and only if it's the 0 function almost everywhere. Okay, so
I think also in vector spaces the 0 element should be unique.
the 0 element should be?
Unique.
Yes.
I have a comment about this other direction. We don't need it because it just follows by the first action that we choose lambda equals 0.
Yes, that's perfectly true. I am not in the business here of finding the least possible sets of axioms. There's always something that follows from the other, but that's okay. I just wanted to get the general thing, right? So this is what matters. So remember, LP, you have to look at modulo the sets of sets of measure 0, okay? So if two functions are the same, if they differ only on a set of measures, then this statement is not true. The third property to become a norm is the triangle inequality. It's the most important thing, which is we have to prove this inequality. Okay, in principle, this is not obvious at all. Okay, this is sometimes known as Minkowski's inequality. Whenever you hear the term Minkowski's inequality, it's nothing more than the triangle inequality in some context. Now you see. I wanted to show you two proofs of this fact. One is the proof from the book, that I could not do it last night when I was on the bus. I said, how do you prove this thing? I said, down to prove it. I could prove it, but then I looked at the book. Oh, there is this nice trick. And so the first proof of this is let's prove Minkowski triangle inequality. Of course, if p is equal to 1 or p is equal to infinity, it is easy, right? P equals to 1 is just a consequence of the pointwise inequality, that f of x plus g of x loses to f of x plus g of x. Okay, and p equals infinity is just that if you take the supremum of f plus g loses to the supremum of f plus the supremum of g. Right? Whenever you have two functions and you add them up, the supremum of the sum loses to the supremum of f plus the supremum of g. Essentially because these supremums might not have been attained at the same point. So this inequality is generally higher. So if this function is less than 3 everywhere, if this function is less than 5 everywhere, of course the sum is less than 8. But it might not actually attain that 8 if the 3 and the 5 are not being attained at the same point. Okay, but this is, so the case is p equals 1 and p equals infinity. it's easy. I'll let you guys think about the details if you didn't get it here. Now the case 1 less than p less than infinity is what matters. And one can argue like this. You can start writing your norm f plus g to the p. You can write it as the integral of f plus g to the p minus 1 times f plus g. Here you break, so this is less than or equal than f plus g to the p minus 1 times, well, modulus of f plus modulus of g. Remember, everything here is at a point x, okay? Point x, point x, point x. This is equal to integral of f plus g to the p minus 1 of x plus integral of f plus g to the p minus 1 modulus of g.
Hildesheim quantity.
Hmm?
We can use from Hildesheim quantity.
Yes. Now you use holder because recall that 1 over p plus 1 over p prime is 1. So this p prime is actually p over p minus 1 if you solve it. So this function here, f plus g raised to the power p minus 1 is a function that belongs to LP prime. This function raised to this power belongs to LP prime. When I raise it to p prime, I will just cancel p minus 1, and it will be raised to the p. So if here I use holder, what I get is, again, holder was for the integral of f times a g. This is my f, this is my g. Okay? So I get integral of f plus g raised to, say, p minus 1 p prime. Let me write it very slowly. Integral of f to the p over p. So this is holder with exponents p and p prime. And then the other one, same thing. And what is this thing here now? This is f plus g, as I observed here, this is just p minus 1 times p prime, it's just p. So this is the LP norm of f this is the LP norm of f plus g. The LP norm would have a 1 over p on top. So I have to say that this is p over p prime to make it appear 1 over p prime. Okay? But p over p prime is just p minus 1. This is just p minus 1. This is this thing. This thing appears here, and here the same guy multiplies norm of fp plus norm of g. All right. And this is the inequality, guys, because we started from the norm p raised to the p power. Norm p raised to the p power loses to the norm p raised to p minus 1 times this, so you just cancel this and you just get 1. And you get exactly the triangle inequality. Beautiful proof, very clean, but if you forgot this trick, like I forgot last night, you're in bad shape. Is this the only way to approach this problem? Absolutely not. So let's think about another way to prove the triangle inequality. You see, one thing that we get from Holder is this this duality statement for the LP norm. And we will talk about, in this course, about dual spaces, and we will prove rigorously that the dual space of LP is the LP prime, and so on and so forth. But as of now, let me just present to you a very innocent statement, and which, with the tools that we have developed today, we already know how to prove. And this basic statement is the following, that the norm LP of any function f is just the supremum of the integral f times g, supremum over what? Over all functions g belonging to LP prime, such that the norm LP prime of g is 1. Okay? So keep this fact in mind. Whenever you want to, I don't want to say linearize the norm, but whenever you want to think about the norm as a linear thing, you know, see, it's just the supremum of f times g, where g is in a certain class of functions. This is very nice.
Sorry, can I ask why dual? Because
why
duality?
Why duality? We will see later in this course that the space, this is a particular case of a more general space of general statement of duality. For every Banach space X, there's the so-called dual space X star, X of the functionals, yes. So the linear, the functions in LP prime, they act as functionals on the space LP by this integral. And so this is a particular case of this statement. We will come back to that. But as of now, since everything is just integrals, if you don't know what the dual space is, there's no problem. Just keep this in fact, and we can actually prove this, right? So let us prove that both sides are the same. So you have on one side you have the LP norm of f, on the other side you have the supremum of certain integral over a certain class of functions. So what I have to prove is that this guy is less than this, and then this guy is less than this, and then they're both the same, okay? So first of all, if I take any of these integrals, integral of fg, I use Holder, right? So I use Holder, and I find that this is less than or equal to the LP norm of f, the LP prime norm of g, and the LP prime norm of g is 1, so this is equal to just the LP norm of f. So for any function g, for any g with gp prime being 1, this inequality is true. For any g in LP prime with the LP prime norm 1, this integral of fg always loses to this guy. So the supremum on the left-hand side keeps losing to this guy. Okay? So this implies that the supremum, so if for all the functions it loses, it doesn't matter if you take the supremum of all of these functions, such g minus 1, it will keep losing. Okay? So we prove that this right-hand side loses to the left-hand side. This is one. The second part of this statement is to actually prove that they are the same. So I'm proving that this guy loses to this one. To actually prove that they're the same, I have to actually find a function g that will make it, that will realize the equality. And the trick, the nice function g would be what? Would be something related to f. So now you take g as being what? As being the
absolute value of f.
Yes, so I want to say absolute value of f of x
To the power
p minus 1, perhaps times the signum of f of x, because here my functions can be positive or negative. So I'm going to take absolute value of f of x to the p minus 1 times the signum of f. This is just a 1 if f is positive, minus 1 if f of x is negative. Well, this is going to be my g. And I will divide by the LP norm of this guy. So by the
to the power p minus 1.
so when I take the LP norm of this guy, yes, so I'm going to divide this by LP prime norm to power P. No, just this, right? So this will have norm 1. Is that correct? This will have norm P prime 1. Right? It's this function divided by its LP prime norm. This will have P prime norm 1. Okay? So if you plug in this function here, you see, this thing here, okay, so first of all, this observation here, this G has P prime norm 1, we agree? Because it's just a function divided by its P prime divided by its norm. So it has norm 1. This function, actually, G belongs to LP prime. Remember, when I have f to the p minus 1 raised to p prime, this will be just f raised to the p. Alright? So, and then you do the computations here and you conclude that when you put on the right hand side the integral of f times this g is just, the top will be just the integral of modulus of f to the p, and the bottom will be just this LP prime norm of this guy. Let's just do the computation. What's the LP prime norm of this guy here? I think we did that computation before, so it's going to be just the LP norm of f raised to the p minus 1. Okay? So this is essentially the LP prime norm of f raised to the p, the LP prime norm of p norm of f to the p minus 1, which is just so there's this magic function here, g, that does the job. Okay? So we have proved our claim. The LP norm can always be imagined as a sup over certain integrals of f against g and g in this space. Okay? So somehow we actually used the same sort of line of thought here, but this is a little bit more natural. I mean, just this statement. Now, just have this statement in mind. Let's prove it again, the triangle inequality. Let's prove it again, the triangle inequality. And then we'll stop after that.
It just follows from this supremum f plus g is less than...
Absolutely, then it becomes trivial, right? So second proof of the triangle inequality is that f plus g raised to the LP norm is just the supremum over certain functions h with p prime norm 1 of the integral of f plus g against this h. Right? Which loses, so the supremum of the sum of two things loses to the supremum of the sum of the supremums. Right? So I'm just using here the supremum of two quantities, A and B, loses to the supremum of A plus the supremum of B. Whatever the supremum is taken over, in whichever class it's taken over. But then, by definition, this is equal to the LP norm of f plus LP prime norm of f. And this is Minkowski's inequality. Alright? So much cleaner, much simpler once you recall the duality state. So, okay, we have proved that these guys are LP are vector spaces. We have understood today what Holder inequality is.
The type should be B.
Should be B, right? Thank you. We have seen Holder's inequality. Now we have proved that it's actually a normed vector space, that this in fact is a norm. It satisfies the triangle inequality, also known as Minkowski's inequality. What was left that I'll leave to do as an exercise for you guys to do is to actually prove that the LP space of a certain omega is actually a Banach space. Well, which actually means to prove there is a complete norm vector space. We actually proved that it's a vector space, we proved that it's a non-vector space. I want you to prove that it's complete. Complete, recall, means that every Cauchy sequence has a limit. So, Cauchy sequences have limit. Have a limit, and the limit belongs to the space, right? So a Cauchy sequence is a sequence of Fn such that, well, for any epsilon bigger than 0, there exists big N such that if m and n are bigger than big N, then the norm of Fm minus Fn is this terms. Okay, so for any epsilon bigger than 0, there exists a big N depending on epsilon such that for any two indexes in the sequence which are bigger than this big N, their distance measured in the norm of the space that they're evaluating, so their LP norm, is less than epsilon. So if I give you a sequence of this form, you have to prove it to me that it converges to a function f, and this function is in this space. So take a look at this proof.
For P bigger than 1, yes.
It's for all p's, right? 1 less than p less than infinity. My p here is always bigger or equal than 1, okay? It makes sense to talk about LP spaces for p less than 1, but these are not Banach spaces and I won't be talking too much about this. I don't find it that interesting. But this is for all p's between 1 and infinity. Okay? So think about this problem. See if you can try to do it yourselves. Otherwise, you can take a look at the book and read and get to know the proof. This goes a little bit of what I wanted to talk to you about today about LP spaces. Next class, next Wednesday, remember, at 4, we will continue and discuss a little bit about dense subsets and how to approximate functions in LP. Okay, so this is enough for our first class. Hope you guys had a good time. If any questions, just look for me, okay? Thank you guys, have a good weekend everyone. Should I stop here?